All right, welcome to nuclear chemistry. This is our first lecture in nuclear chemistry, and I fully expect you to be taking notes as you listen to this lecture for the first time. And if it's your second time, hopefully you're refining your notes and making them better. So, as I navigate my way to where we need to be, what is nuclear chemistry? We started off our matter discussions with what is chemistry. Nuclear chemistry is the study of the atomic nucleus and the changes that the nucleus can undergo. We use a lot of terms. We just got through defining a bunch of terms about the atom and the atomic structure part of the unit. Now we need to talk about some terms that are exclusive to physicists typically. Speak of isotopes of elements as nuclides and not just isotopes. And it's meant to describe the state of the nucleus. It doesn't pay much attention to the electrons because physicists who study the atom are more concerned with the nucleus. So they talk about it as nuclides. You might also see the term nucleon, but they all imply the same thing, is a certain layout of a nucleus of an atom. But this unit is all about that tiny dot where the protons and neutrons live called the nucleus. And really and truly, it's kind of an oxymoron to say nuclear chemistry because a lot of the chemistry we understand takes place because of the changes that electrons undergo, not really much to do with nucleus. But the nucleus is a big factor, and we have to give it some attention so we understand fully how it works. So that's what this unit is about. Most known isotopes to humanity are radioactive. There's, I think, 600 odd known isotopes out there. I think there's 114 plus elements. There's almost 700 almost 700 isotopes, most of which are radioactive. Tells us that for the most part, if you think about all the atoms that are out there, radioactivity is common. Radioactivity literally means for the nucleus to decay and lose energy as it does so. Radioactive elements naturally break down into smaller elements and release particles and/or energy in the process. The reasons nuclei break down is because they have an unstable nucleus, meaning their proton to neutron ratio or neutron to proton ratio is not conducive to maintaining stability. When elements decay, they decay to form a new element that is more stable, with a more stable proton to neutron ratio or neutron to proton ratio. This video is a song that we will play in class. A term that's important to know is transuranium element, and it's a scientifically friendly term because it's the meaning is in the word. Transuranium elements. And it's elements that are beyond uranium on the periodic table. Above atomic number 22, largely elements that are on the periodic table beyond 92 are not found in nature. They may be found in trace amounts as they're decaying from larger other elements in nature, but by and large they are not naturally going to appear on Earth. For the most part, they were synthesized in nuclear reactors and in particle accelerators somewhere around the globe, and they existed very much momentarily in decay almost as quickly as they became into smaller, more stable nuclides or atoms. A little history. Wilhelm Röntgen found that invisible rays were emitted when electrons bombarded the surface of certain materials. And he went on to become the founder, one of the founders and initiators of X-ray imaging. And so radiologists dig Wilhelm Röntgen. So if any of you are considering medicine or radiology, you and this guy will become very good friends. Henri Becquerel accidentally discovered that phosphorescent uranium salts produce spontaneous emissions that darken photographic plates. Now, that doesn't mean much to you in your iPhone, but back in the day when photography consisted of using light to change the chemical composition of a silver material, the fact that they could do it without sunlight was pretty groundbreaking. So Becquerel's research found that they could darken photographic plates without the benefit of visible light. So there you see a little bit of the beginnings of starting to understand radiation other than that we knew of light. Marie Curie, arguably the biggest contributor to nuclear history, she isolated components emitting those invisible rays, particularly uranium. She defined the term radioactivity as the process by which particles give off rays. She defined radiation as the penetrating rays and particles that a radioactive source emits. She discovered herself the elements polonium and radium on the periodic table, and element 96 is named for her. She died of, you probably don't know what this means, but we're going to give it the exact definition, aplastic anemia, or more specifically, radiation poisoning. Of course, working around radioactive materials, before you fully understand the wealth of their danger, she was exposed to large amounts of radiation over the course of her career. She died at a relatively normal age. She died in her late 60s, but radiation poisoning was a contributing factor to her death. Terms that we need to understand that are specific to nuclear chemistry. Radioisotopes. Isotopes of atoms. Ooh, look at that. You can take this one time. Isotopes of atoms with unstable nuclei is a radioisotope, short for radioactive isotope. Like we said a few minutes ago, most isotopes that are known to be are radioactive. That doesn't mean most atoms are radioactive. Most atoms are stable. But of all the known isotopes in existence on the planet Earth and beyond, most of them are unstable, meaning too many or too few neutrons in the nucleus. Radioactive decay is unstable nuclei emit energy by emitting radiation to attain a more stable atomic configuration. This is a spontaneous process, and this is why mathematicians love it. It's predictable. And so a lot of the privilege of teaching you guys log-based work falls on our math teachers' shoulders, while in chemistry we'll still teach it to you, though, because we like you and we think we teach it just as well, if not better. So this is an example of 3 different isotopes of carbon: carbon 12, 13, and 14. Carbon 12, 6 protons, 6 neutrons, perfectly stable. Most of the carbon you are made of is made of this. Carbon 13 contains 1 more neutron, still relatively stable. Very small percentage of the carbon in you is made of this. And then finally, carbon 14. Get a full 8 neutrons here. I'm going to put 7 neutrons. When I put it in with a 0, that means a neutron. 6 neutrons here, 8 neutrons here, and you can see it in the blue dots. But the trick is carbon 14 is unstable, and it also happens to be one of the ways we can gauge the age of something that is dead on Earth. We're all carbon-based life forms. All carbon-based life forms have a very predictable amount of carbon 14 in them by percent mass. But once you die, you stop collecting carbon 14. However, the carbon 14 in you continues to slowly decay over time. So for about 60,000 years after you're dead, we can tell how long you've been dead by analyzing the parts of your corpse for carbon 14. I know it's fascinating. You may be asking yourself, Mr. Crump, why didn't you write number of protons there? Because it's all carbon. All carbon has 6 protons. No need to get too specific. Nuclear stability. We have a couple ways we can analyze stability. The first way is just simply looking at its atomic number. Assess atomic number for stability. It's stable if its nucleus won't spontaneously decay. Elements with atomic number 1 to 20 have at least one isotope that's very stable. 1-to-1 proton to neutron ratio. There it is written right there. An example is carbon 12. 99% of the carbon in you is carbon 12, okay? And it's stable. So chances are an atom of carbon is very stable. Elements 21 to 83 are what are called somewhat stable or metastable, meaning that they do have radioactive isotopes, but by and large, most atoms of elements 21 to 83 are going to be stable. There are exceptions at this point, okay? There's a few elements, or one element in particular that's man-made, element 46, I think, technetium. It's a man-made element that's not terribly stable. It's got uses, though. Anyway, the proton-neutron ratio, elements 21 to 83, tends to be about 2 to 3 instead of 1 to 1. But like I said, most of them are stable for the most part. Bismuth is our last guaranteed possible stable element. And you may have had bismuth in your Pepto-Bismol when your stomach got upset last. Pepto-Bismol contains bismuth, stable bismuth. Beyond element 83, 84 and up, do not have a stable isotope and are considered unstable and radioactive. Okay? Everything 84 and up is considered unstable and radioactive. There's no discussion beyond that. Proton to neutron ratio tends to be 1 to greater than 2. Uranium and plutonium, two examples of elements that are known to be unstable. This graphic up here is kind of dramatic. That's fission. Fission, for all it's worth in the history of World War and bombs, fission as atoms go is pretty rare. So don't get all lovey-dovey with the idea of fission being the big topic here, although it is discussed. This is an awesome table, but you have to breathe it in. The table tells you the number of stable isotopes. And what I want you to see is what we talked about in the past 3 slides. Elements up to 1 through 20, largely stable. Okay? A few of them have just one stable isotope, but usually that's about 99% of the isotope out there. Elements 21 to 83 for the most part are stable, but once you get to 80, this is technically untrue. Bismuth, though it is technically considered unstable, its half-life is so long that it's perfectly stable, on the order of millions and millions of years for each atom to decay and lose energy. So bismuth is considered stable. So in this graphic, I'm going to ask you to please forgive me. Let's consider bismuth stable. Starting with polonium, though, 0 stable isotopes. Okay? 0 stable isotopes. And like I said, the exceptions in 21 to 83, technetium and promethium, those are both man-made unstable isotopes. Did I say promethium? Yeah, that's correct. So let's move along. Talk about the stability of nuclides when you're assessing. Instead of looking at just atomic number, we look at the arrangement of the nucleus. Now, this is not as general. This is a much more specific method. For any nuclide, and again, if a nuclide is a physicist isotope, we can compare proton to neutron ratio to make generalizations. We can also use those numbers to give us a clue. If our nucleus contains an odd number of neutrons and protons, like hydrogen 2 is 1 proton and 1 neutron. Those are each odd numbers. There are 4 different atoms that have odd number of protons, odd number of neutrons, or 4 nuclides, pardon me, that have odd neutrons, odd protons that are considered stable. Anything else is unstable. Okay? So something that were to have, say for example, 9 protons and 9 neutrons is going to be unstable. All right? That would be chlorine. Odd numbers, both. These are the 4 stable nuclides. You're going to need to know those. Hydrogen 2, lithium 6, boron 10, and nitrogen 14. Anything above nitrogen 14, odd, is unstable. And again, odd means number of protons, number of neutrons are odd. Now, even number of protons, even number of neutrons. So if the mass number of the nuclide is greater than 3 AMU, different from the periodic table average mass, the nuclide is unstable. So let's give an example here. If we have, for example, let's take carbon-16. Now this is a fictitious, pardon me, that's a terrible way to write that. Carbon-16. 16 and 6, and that's carbon. Terrible, terrible shorthand notation. In carbon-16 we have 6 protons, and we have 10 neutrons. Okay? The average atomic mass of carbon is 12.01. If the nuclide number is greater than 3 AMU different from the rounded periodic table mass 12, 16, and it's even, then this would be unstable. So if it's even, our mass number of our nuclide is 3 or more different than the rounded periodic table mass, the nuclide is unstable. Now let's look at odd even or even odd. Now if our proton number, neutron number is some combination of odd even, one is even, one is odd, then all the grace we get is 1 AMU difference. Calcium 45 is our example. Calcium, atomic number 20, 45. Oops, my handwriting is garbage today. Welcome back. Sorry to pause there. We were talking about calcium 42. Calcium's average atomic mass on the periodic table is something like 40.08 AMU. And if your nuclide mass is greater than 1 different from your average atomic mass, then your nuclide, when it's even odd, and it's supposed to be a 5, like I said a minute ago. Sorry for not fixing that. 45. Clearly, it's almost 4.92 greater than the average atomic mass. Then calcium 45 must be unstable. Okay. So we had 3 conditions: odd, odd. And there were 4 possibilities that are stable. Even, which allows us to have a fudge factor of about 3 AMU difference between the nuclide and the average atomic mass. And then odd, even, which gives us the very small fudge factor of about 1 AMU difference to predict instability. So those 3 factors help us determine the stability of a nuclide, okay, a specific isotope. So looking back, when somebody asks and talks to you about an element, and they talk about an element between 1 and 20, you can say with certainty that it's probably stable. Does that mean all the isotopes are stable? No. It just means that when we talk about them in terms of their location on the periodic table, then we have a general idea of stability. Okay, so these 3 slides dealt with general idea of stability based on atomic number. These 3 slides spoke about specific isotopes and what determines stability of those isotopes. And these 3 little rules help us determine if a specific nuclide is stable. And we're going to stop right there. We will talk about transmutation in the next visit. It's been awesome. See you on the next one.